Hey, here we are, Math 2265. We'll be covering the bulk of section 9.5 today, several examples for us to look at. And although we end this lesson with several examples from the calculator, TI-83, we start off this first one with calculator use. I'm not able to share my screen with you as far as that's concerned, but I have run through this, and they do a very good job of explaining step by step what to do, even if you don't happen to need that. So to look at this particular one, and we can see how they set it up. The mean throwing distance of a football for Marco, a high school freshman quarterback, is 40 yards. Standard deviation, 2 yards. Team coach tells Marco to adjust his grip to get more distance. The coach records the distance for 20 throws, and for those throws, his distance was 45 yards. Coach thought the different grip helped Marco throw faster than 40 yards, farther than 40 yards rather. So conduct a hypothesis test, and alpha 0.05, the usual. The standard, I should say. It isn't always going to be that case. Assume the throwing distance for footballs are normally distributed. So what we'll do is we'll definitely be using the z-test here. And so they say to press stat, arrow over to test, press 1, z-test, arrow over to stats and press enter, arrow down and enter 40 from u0, the null hypothesis, 2 for sigma, 45 for x bar, the sample mean, and 20 for the sample size n. Arrow down to mu, the alternative hypothesis, and set it as one of these. And it turns out we're looking for it to be greater than 40, and so 45. And we did say that we think it's going to be improved. Further throwing is an improvement, of course. And so put the greater than down, please. Press enter. Arrow down to calculate, and then press enter, and they'll give you the data. And here's the data it'll give you. It'll give you a z-value of 11.18, which is way off the scale. Our scale pretty much ends at 3.5. The p-value is extremely low, 2.6 times 10 to the minus 29th power. That's pretty close to zero. Imagine all those decimal places. Yeah, it's technically not zero, but it's way less than alpha, which is 0.05. So this is a pretty solid conclusion where you strongly reject HO. P-value is virtually zero. Z-value is off the charts. This didn't happen due to chance, the 45 yards. There's something going on. And perhaps the grip adjustment was it, or maybe he just recovered from an injury. There could be other explanations. We can't address that. But we can say that that 45 is a lot bigger than 40, no doubt about it. Even with only 20 throws, that is enough to guarantee a very large z, a very tiny p-value, which says this is so rare to have happened by absolute chance that it could not have happened due to random chance. Okay, let's move on. And by the way, here's the historical note. This is what I'm kind of used to, solving for z, getting z involved. I'll probably do that here and there. I don't have the advantage of a pen. In fact, I can't even expand the screen for some reason. I'm not sure why that's not expanding. So I hope you can read this. My pad will not let me expand today. I don't know why. But we do have the fact that the z-score would be done. We find the difference between the sample mean and the true mean, population mean, divided by the standard error, and we'd get a value of z. And basically, you probably don't need a value of z unless, of course, I request a value of z, which then your calculator will give you, or simple formula could also give it to you as well. So they do look at a 0.05 in the normal table. This happens to be a left tail test that is not connected to the last example. So they have found a critical value of z, which is the way they used to do it and still do a little bit, but not so much anymore. Minus 1.645 is the number you'd have to beat. That is, be less than, in a less than hypothesis. HO would be equals to a certain number, and HA would be less than a certain number for your value. And this will not be proportional, just be a regular sample mean with a known standard deviation. Yes, we have 16, etc., and mu 16.43. Well, anyway, the test value we got to 3 decimals was about 2.09 negative, and that is in the critical region, the region where we reject HO. It's in the dark zone, and the p-value shows how rare it is. It would happen almost 2% of the time due to random chance. And if we're listing 5% as our criteria, that number is less. Wouldn't be less than 0.01 or less than some other numbers that are small, but it is less on this particular test. And these are always parallel tests. If the p-value is less than alpha, then your z would have to be more extreme than the particular value of z. So they go together. We're just not really focused so much on the z's in this particular book. Okay, it's really bugging me why I can't get this to I've done something wrong with the screen. I don't know what. So anyway, I hope you can zoom on your end and see, or at least refer to your book and just listen to my comments. That's another way to go. So in this particular example, we have a football coach, and this is with raw data, which you could do by typing in the raw data into your calculator. And what they're looking for is they're saying the mean weight that the players can bench press is 275 pounds and a standard deviation of 55 pounds. That's what we wound up with. But then we take some samples. 3 of his players thought the mean weight was actually more than 275. So yes, they asked 30 of their teammates for their estimated maximum lift. This is estimated now. Maybe, well, hopefully, I'd rather see it recorded because exaggerations can become parts of estimates. The data range from 205 all the way up to 385, which doesn't tell you too much. And here's the actual weights, kind of in order with their frequencies as well. There's as many as 5 people that did a particular weight. Well, anyway, this time they want an alpha of 2.5%, a very strange choice of alpha. But that's a natural consequence of a 95% confidence interval or a two-tail test that happens to have the remaining 5% divided in 2. So you get 2.5% in each tail. So this is not unheard of. Let's click on the solution if it'll give it to me. Yes, it does. Okay, it's just a little bit small. I'm not sure why. Anyway, let's see if we can. Oh, there we go. Finally, I got it to kick in. This pad is getting worn out. So we set the hypothesis test, and it's about a mean weight. So yes, single per population mean. We're not going to really know this is going to be a, let's see, what kind of test? This is going to be a z-test. Apparently they're going to go ahead and use the z-test. We're not, yeah, sigma is equal to 55. Why do we know that? Always use sigma if you know it. You may not always know it, but that's what they have. So this is a z-test, not a t-test. I was temporarily fooled. But a right tail test, because they said it's going to be greater than 275. So he's just going to run it through the sample and see if it really is big enough to be considered greater than 275. And by the way, 276 would not cut it, but maybe 350 would, that kind of thing. So X bar is the mean weight in pounds lifted by the football players based on this sample that we have. We do have sigma known, however. They did say right off the top that he records the mean weight over the period of time, 275, standard deviation of 55. So they measure it again just to see if they get a discrepancy here. And so here's the distribution, mean 275, and the standard error, which is really just sigma over square root of n, sometimes s over square root of n. That works out to be 10.04. So it's pretty much 10, not 55, but 10. Now, here comes the sample. It's 286 pounds. That's about 11 pounds more than what they found. Is that enough? It's hard to say. Always use sigma if you know it. It's often not known. We, of course, will assume that mu is equal to 275 unless our data shows us otherwise. So the calculator can help us get the p-value, although one could get it from the z-value and creative use of the table. Z is doable. T is not really doable. But anyway, P is using the normal distribution for a mean, use a sample mean, there's a table, etc. So they do find that the z-value works out to be 1.12. How did I get it? I took the value of x bar, 286.2, subtracted away the mean, 275, and divided by a number barely over 10, 10.04. That z-value, in case you care, is 1.12, a moderate value of z, and that could be placed right here on the z-scale. Instead of an x-bar scale, you can say a z-scale. And then to the right of that, why do we say to the right of it? We have a right tail test, and p-value always goes in a more extreme direction. P-values head to the tails. Two-tail test, it heads to both of them. That's why you could double it, but the calculator will do that for you. Here, if you were doing the old-fashioned method, you would simply look and see what's over here that's larger than 286.2. the standard error is only 10, and it's only about 11 off, so that's why the z-value is only about a 1. And that means there's still 13% left to go, which is a pretty high number. This is not a rare situation. 0.13 is greater, 0.1323 is greater than 0.025. This is pretty rare. There's not much going on. So if HO is true, there's a 13% probability that the football players could just by themselves, due to random chance, lift more than the 275. That is 286 is what they got. And so, lifting more than 286 pounds just isn't very rare. We'd rather see this number to be lower than 0.025, and it isn't. It's commonplace. Because it's commonplace, HO gets to stay. This isn't big enough to matter. It may seem like it, but that's only moved about 1 standard deviation away from the center, and that isn't enough. If this had been a tiny standard error, like if we'd done a sample of like 100 players or something like that, maybe that'd change. Or maybe the standard deviation was smaller. There could be some changes, but there wasn't enough there. And yes, the calculator can certainly do it for you. And you get your z-value of 1.11. I got 1.12. That's round-off error apparently. And then the p-value 0.1331, which doesn't quite match this value here. So yeah, they've got a little bit more accuracy in the calculator. So do not be worried about minor discrepancies like that. They say a little different from the previous calculation, because we use the sample mean rounded to 1 decimal place instead of the data. So that's the problem. Always best to use the raw data when you have it available. Okay, so we would keep HO. In other words, mu is still about 275. It has not changed. It hasn't moved the needle enough. That's the conclusion. And I don't have the ability to write on the page right now. I apologize for that. Next time I'll do a live Zoom meeting for just me, and then I'll be able to do it. I just didn't get my act together today on that one. Statistics students, though, in this new example, believe the mean score in their first test is 65, and an instructor thinks the mean is higher than that. And he samples, it seems like he could probably get the entire population, but he samples 10 students and records the scores. And here they are, raw data, which can be typed in. And alpha 0.05, 5% level of significance, that's what alpha is. The probability of getting a type 1 error maxes out at 5%, no more than that. Data are assumed to be from normal, of course, and so here's your alpha again, and here we have a right tail test again. Your book is very fond of right tail tests. I will also give left tail and two tail tests, just warning you here, for those of you digging deep into the lecture here. I always like to give little clues of what's happening on the test. Yeah, so the instructor thinks it's higher. We use a greater than sign. And so X bar is the average score in the first stats test. And so there's no population standard deviation given. It's simply the raw data. So we would have to use the t distribution because we do not have a sigma given. That's like a historical norm that people know about. But we go from the data and we find various things. So they will give us the list. Here it is. The actual X bar was 67, which is a little higher than 65. Question is that 2 points really enough? Maybe it is, even though we don't have the standard deviation available right now. According to the calculator, the p-value is down to about 0.04, about a 4% chance of a number happening like this just by random chance. It could happen on its own 4% of the time. Because that number is less than the 5% chance, we can now say, well, this is what they're saying. If HO is true, there's roughly a 4% chance that the sample mean is 65 or more. But that was less than alpha. They've written this backwards, in my opinion. I'd rather compare p-value to alpha, not the other way around, but it's just the way I've done it for years. This book has to go against the grain, of course. No perfect book out there. Well, anyway, p-value is less than alpha. We reject HO. Something remarkable has occurred, not extremely remarkable, but we tried to beat 5%, and we did. We got it down to 4% on the p-value, that is. Probability of a number happening to be that large just by random chance. The shading is not very accurate. Don't worry about it. Any graphs that you would do not have to be done to any rigorous scale. But 67, of course, is greater than 65, and you have to shade at the tail, or in some cases tails. But that would be about it. So we reject u equals 65. In other words, the average test score is more than 65. Something here did move the needle. We got a low p-value. That's rare. Low enough versus 0.05. And so we got to move the needle over. We reject the status quo. We get to go with the alternative. Since HO is rejected, by default, we will look at the alternative as being something we don't exactly accept, but we're certainly steering our preference in that direction. So I have to be careful with my wording here because of all the legalistic dialogue going on and the exactness of how it's said. But we are leaning strongly towards the average test score being more than 65. Of course, I only got 10 on the sample. The power of the test isn't very strong. So the conclusion, at a 5% level of significance, the typical one, the data shows sufficient evidence that the mean test score is more than 65, just as the instructor thought. So the instructor apparently knows everything. Well, not exactly. And the p-value could easily be calculated. So they have done that. In fact, you could calculate the z-score, which I happened to get here somewhere. Where did I put it? No, this time I did not actually calculate the z-score, but it would not be very hard to find. That number looks like it's around a 2 for the z. Yeah, that would be a difference of 2 divided by the standard deviation, which we do not have in front of us, though. So that's what the calculator would be hiding a bit of information there, but one could easily find it there. Oh, by the way, the t-value, not z-value, is 1.978. Usually t is done with 3 decimal places. And even more importantly is the p, which is less than 5%, very close to 4%. And okay, that's how that goes. And they have a try it, which I will let you enjoy if you would like. I hope you try some of these on your own. This is with the raw data, so be sure you have the data item clicked on. In the next example, 9.17, June believes that 50% of first-time brides in the U.S. are younger than their grooms. She performs a hypothesis test to see if it's either the same or different from 50%. Now, they actually were very nice to you in that they said different from. They didn't say greater than, they didn't say lesser than. Sometimes they just say is 50%, and that's a two-tailed test because there's simply nothing else said. But they were kind, and they emphasized the fact that this is a two-tailed test. I may or may not do that on the final, just letting you know this. We don't actually have to say or different from. Just simply do not include the greater than, do not include the lesser than, and then you get both, 2 for the price of 1, two-tailed test, I guess. So 100 first-time brides are sampled. 53 reply they're younger than their grooms. Is 53 out of 100 enough to really matter, to show a difference? Of course, alpha will be 1%, 0.01. Okay, so yes, that's the very first thing to start with, is alpha is 0.01. And of course, we have a single population proportion, which will be z. I don't think we even looked at NP and NQ, but they will be sufficient to be enough. In fact, with 50% from the hypothesis, which is what we have to use, we do not use the sample p. 50% of 100 is 50, and that is greater than 5. And Q is exactly the same, being a 50-50 split. So yeah, we are definitely over the line, binomially speaking. So the words is the same, or even same or different from, tells you it's a two-tailed test, which means we have to put in the not equal sign on the alternative hypothesis, which is unanimously done across the board, across the margins of every single book. We will not have any dispute about that. So P prime, I'm used to saying a P hat, but P prime is fine. Percent of all first-time brides who are younger than their grooms, and 53 were younger. I think it used to be more than that. It used to be a much stronger number than that, but hard to say exactly. The problem doesn't mention a mean, but it does talk about proportion, so we can use that. And it'll be normally done with P being the mean, 0.5, and then we have to get this standard error, which binomially speaking will be the square root of 0.5 times 0.5 over 100, and that number works out to be, strangely, 0.25 over 100, which if you take the square root is exactly 0.05. So you got 0.5, I don't like the leading zero, and 0.05 for the standard error, exactly 1/10 of the mean. Well, anyway, n is 100. So let's calculate the p-value, and so let's see what we would have. For a two-tailed test, we are interested in the p-value being at least as extreme as the value. So I'm going to focus on the 0.53 and above, but because it's a two-tailed test, we do actually have to go 3 places away from the mean on the left side as well. Here's the picture. And yes, we did get P prime to be 53%. That was kind of easy, 53 over 100, 0.53. And the right tail is pretty easy to see. We're looking for things that are more extreme than that cover the different from genre. The stuff in the middle, which is relatively close to 50%, is clearly the equal sign. I'm trying to draw an equal sign with a pen with no ink in it. But then, because it's two-tailed test, we look at the difference, 3% difference, 0.03, go to the left side and say that if it was like, say, 0.46, that would also be different. Anything to the left of 0.47 is different enough to match the other difference. So here's where the two-tailed test actually can be shown on the diagram. Some people do find this a little bit confusing, but you get used to it after a while. I've never really gone for sketches from this point of view, but yeah, this could work as well. The point is, we get a huge p-value. One could look up a z-value here, which I got to be 0.6, 0.6. When you run the numbers, by the way, in case you want to know, z would equal p prime minus p, all divided by the standard error, square root of pq over n. That's the z formula. When you do that, you find one of them is 0.6 on the positive side, and the other is minus 0.6 on the negative side, both extremely moderate values. This is really not drawn to scale. It would be much tighter around the center. And if you double these numbers, you get to about 0.53. Let's see where it is, 0.5485. That is extremely common. It's very, very easy to get 53 out of 100, or say 47 out of 100, which is exactly equivalent in this two-tailed test to make your 53% or 47%, 0.53, 0.47. And yeah, you'd have more than a 50-50 chance of getting that extreme just by random chance. So this is what I mean. It almost gets confusing when you get large p-values. But we had to compare it versus 0.01. This was not a close call at all. 0.5485 is way bigger than 0.0100. You do not even come close to rejecting HO. You basically love HO here. Please don't even think of rejecting it. So I'll try to say as extremely as I'm allowed to. Yeah, you're going to go with the fact that it's still 50-50. It's kind of like analogous to flipping 100 coins. You expect a fair coin will be 50 out of 100. To get 53 out of 100 on a sample run of 100 coins would be no big deal at all, especially if you're using a two-tailed test. If there's a one-tailed test, it would be half that much. It would be this amount. If you ignored the left tail and only went for the 53 over 100 or larger, even from the myriad standpoint, that still is way bigger than 0.01, 0.2743, let's say. Even on a single basis would be much bigger than 0.01. So you wouldn't have to really worry about that. But because it's two-tailed, we look at the other side, the mirror reflection symmetrically of it, and basically double it. So that's your very large p-value, very common, not even close to rare. So to say it more formally, at the 1% level, or just alpha equal 0.01 is good enough. Sample data do not show sufficient evidence, that's for sure, that the percentage of first-time brides who are younger than their grooms is different from 50-50. You'd have to move the needle over quite a bit. I don't know, 57, 58, I don't remember what the exact numbers are. But of course the calculator can come into play. And here is your z-value. They do reveal that. It's really plus and minus 0.6, which are very moderate numbers, very moderate indeed. And let's take a look at the type 1 error. Type 1 error would be to conclude, by the way, what is a type 1 error? Rejecting HO when HO is really true. That is equivalent to saying we will conclude the proportion of first-time brides who are younger than their grooms is really different than 50%. So we're rejecting HO, when in fact the proportion really is 50%. So we'd be rejecting that, and that's a type 1 error. That's what the alpha is supposed to get down to 0.01 on. And type 2, we're not too worried about it, but just flips the script here, says, well, I don't need to review that, but that they didn't even ask for it. They're just kind of filling it in. We're just not calculating beta here. That's something even the calculator doesn't do easily. So let's not go there. But they, by the way, not say there's not enough evidence that the younger is different than 50%, but really it does differ from 50%. So we'd kind of say, oh, it's close to 50-50, but actually it did differ, and that would be a beta error. Well, anyway, that's not really relevant right here. And the try it, you can certainly look at that. That's not a difficult one. Maybe I'll come back and do some more of these, or find some problems from the other book if I feel up to it. And they are not really going in a tangential direction away from our main line here. That's one advantage of the workbook. It does seem to stick to the script most of the time. And I do enjoy that, actually. Okay, here's example 918. Here's a consumer group suspecting that the proportion of households that have 3 cell phones is 30%. Okay, whatever. A cell phone company has reason to believe that it is not 30%. Didn't say greater, didn't say, they could have said is 30%. It could have said any one of several things. But this is one of those two-tailed test situations. Before they start a big advertising campaign, they do a hypothesis test and they survey 150 households, and that result shows 43 have at least, well, exactly 3 cell phones. So let's be sure we read this correctly. 4 and 5 don't count. 0, 1, and 2 don't count either. So we can go through and take a look at the solution as we start to look at the problems. Let's see. Yeah, they kind of skipped part A on this. Another little misprint here. I found misprints in the other book for the other class earlier. We set up the hypothesis test. This should be pretty easy. We're talking percentage, so don't go to mean. Go to proportion. Proportion is tailor-made for percentages. However, it is not a good idea to put the 30% inside the hypothesis test. It's considered bad form, but it does provide a strong clue so that we're not going to use the mean. We're going to use the proportion instead, and it'll be a z-test again. So we set it equal to 0.3, and then we set the alternative equal, well, not equal to 0.3. And what distribution? Well, we can verify that NP and NQ are greater than 10, and 30% of 150 is 45. That's greater than 10. And, you can do 70%, which is Q, on 150, and that's way more than that. That's 105. That's still greater. So we've got that covered. The book didn't mention that. And so we have our mean, which is the proportion of 0.3. We find the standard error by taking the square root of P times Q over N. So you run those numbers, which I did earlier, found that's equal to 0.0374. So roughly also about almost a tenth, more than a tenth of the mean, but that's no big deal. So 0.0374 is that number in case you needed it. So A is the value that helps determine the p-value is what we got from our sample, sometimes known as p hat, but here we have p prime and x over n. The success is 43 over the total number, 150. And oh, by the way, they forgot to give you that number. It's 0.2867, close to 29%. So it is off by a percent. And the question is that going to make a big difference or not? It seems like 1% doesn't make very much difference to me, but then we do have 150 in our sample, and that could tip the scale a lot quicker because of a larger sample than we sometimes see. What is the success for the problem? Success is finding a household with 3 cell phones. Part C says, what is the level of significance? Did they say anything up here? No, they didn't. So we go for the default 0.05, and that's what they're going to say. It's the preset alpha, the level of the type 1 error we're going to allow. And alpha is not given, so we'll go ahead and use the 0.05. That's just a standard situation, which I guess I could use myself. So those who pay attention will be rewarded for that. Okay, so we do have the graph of the problem, which they don't happen to show. Let's calculate the p-value. Let's see how the p-value would go. Now, the p-value for this two-tailed test is very, very large. I do not have the ability to draw the sketch. I did it in my own book. I wish I could show it to you. But before I do that, let's see how z would turn out. Z would be p prime, which is about 0.2876, minus p, which is 0.30. It's a very small number, about minus 1% on the left side, if you start with the left number, which, well, it's what we're going to do. And so, anyway, we get, well, actually, p would be 0.30. I got that reversed. 0.30 minus 0.2867 gives you about a positive 1%. Well, after you divide by the standard error, which is about 0.0374, you get a very tiny value of z being minus 0.36. It's really plus and minus 0.36 for your z, and that's even narrower a margin than we had before. Looking back here where we do have a sketch, let's just take a quick look here. Here we had z values of plus or minus 0.6. Imagine what happens if it gets to be plus or minus 0.36. It's even narrower, it's even tighter, which drives our p-value up even further. We have a very large dark side here. And this means if the other one was common, this is even more common. Look at that huge p-value. This is becoming almost hard to interpret because this is very easy to do. When you pick stuff at random, you could easily get it outside of outside of those bounds. So Yeah, the p-value is about 72%, way bigger than 0.05. It's even more of a strong case conclusion than before. And of course, we could easily get beyond the 0.30. And we stayed quite clearly next to the BO. The 0.30 is almost a bullseye, as I said. And if it was a bullseye, it was exactly the same. You have a p-value of 1. In the most extreme case, you never, ever see that. But I have seen a value of 0.99 before, a number that was very close to the predicted number. It means your prediction was really good. So p-value is way bigger than alpha. Please don't even come close to rejecting HO, not even close to sufficient evidence to conclude that the deal is not 30%. Yeah, it's 30%. Based on our sample, we're right on top of the 30% with 0.2867. They should have said that. I wish I had the ability to write that down. I'll just keep verbalizing it so you can see how close it was. Driving up the p-value to make a very common scenario and just not even close to being rejected. You love HO here. Keep HO. I might even say accept, but I'll probably get in trouble. So you have to say equals 0.30. And that's what you're going to go with. You're not going to reject that, not even come close to rejecting that. And you have a try it that you can try as well. Maybe I'll get a chance to work on some of these. Now we have a poem. It seems a little weird, but it does boil down to something we can do. So here's a student probably in the guy's class, and so the solution follows the poem, and they basically summarize what's going on here. They say that we're using proportion, so we're using P, normal distribution, and the estimated proportion is the proportion of fleas killed to the total fleas found on Fido, which is such a typical name for a dog. Not exactly. Anyway, we have an alpha 0.01. And they do say that. So anyway, they do say this. I don't have to read the whole thing to you, but the dog has a lot of fleas. They don't come off with ease. As for shampoo, I've tried many types, even one called Bubble Hype. Only killed 25% of the fleas. Turns out that's extra information that we don't really need. Well, actually, I'm wrong. I would take that back. That is pertinent information. We're going to start off with P equaling 0.25. That will be our HO. Now, we'd like to get more fleas than 25%. Notice the word only. So you want to go greater than 0.25 for your alternative. P is greater than 0.25, and the solution will say that. So they go through a few other things and blah, blah, blah. So before we counted 42, and then we found that they got killed 17 of them. So now I was pleased, and here's your alpha 0.01. You must help me figure out use the new shampoo or go without. So if the shampoo is somewhat better, we should go with it. And if it really isn't better, if it's about the same, then there's really no real reason to switch shampoos. You're just going to have to live with whatever you got. So don't worry about this less than or equal to. Just say equal to 0.25. And then the main one, the alternative, is to be greater than 0.25. Okay, P prime is the proportion of fleas that are killed by the new shampoo. We already have on file the old shampoo, 0.25. And yes, that's going to be our mean, our proportion. They're the same thing. The standard error, 0.25 times 0.75 over 42. By the way, that number is 0.0668. And when you run the numbers on Z, Z is equal to P minus P prime over that standard error called square root of PQ over N. When you do that, the Z value is 2.32, and they've given it right here. They gave you 4 decimals. I'm just used to 2 for Z. And then a P value, which you could even find from the table, because this is a one-tail test. You'd be looking only at the right tail, and you just take 1 minus the table value. But probably nobody's using a table unless your battery dies. And that gives you a very tiny p-value, 0.0103. But remember alpha? Alpha was 0.01. This is a different kind of an issue. So explain what the p-value means for this problem. So let's be careful about it. The numbers are pretty close. If the null hypothesis is true, and the proportion really is 0.25, then there's a 0.0103 probability that the sample, the estimated sample proportion, is above 1740 seconds. Where did the 1740 seconds come from? That's from the very end of this little poem. 17 out of 42 was over 40%. So that's information we could have used a little earlier. So let's see, 40% versus 25%. That does look different, doesn't it? Yeah, it does look different. That's 15%, more than 50% above what the other shampoo had. And yet we can find that this would happen randomly by itself due to chance 0.0103 of the time, or that is 1.03% of the time. So here's the sketch. we have a situation here, clearly label, all this kind of stuff. So we put in the 0.040. They've done a lot of things here. They put down the Z, 2.32. They put down the 0.4048, and they're taking a look at what this would be. And they've already found what the p-value is, 0.0103. But the main conclusion is the following. Compare alpha and the p-value. They're so close together. But the thing is, the p-value is actually larger than alpha. So that makes it not so rare. It makes it quote-unquote commonplace as compared to the rigorous standard of alpha. Alpha is 0.01, very rigorous standard. And we barely missed it by just a thread, just a tiny, tiny bit. So we can't reject HO. We have to keep HO. HO says that we'll stay with P equaling 0.25. I don't even care about less than. P would be still equal to 0.25, despite the fact we had 40.5% from our sample over here. That's a surprise. We have a strict standard. We didn't quite make the strict standard. Most other alphas, it would be fine, 0.05, 0.10, anything else, 0.025 even. But in this particular strict case, we missed it. So we don't have enough evidence to switch shampoos. However, it does say this. And as they rephrase it, at alpha 0.01, sample data does not show sufficient evidence that the percentage of fleas that are killed by the new shampoo is that much more than 25%. Yeah, that sounds strange, huh? Because intuitively, almost everybody would say, oh yeah, this is a lot more. Sounds good, but not really. So yeah, that's surprising. But they do say there's, well, we can do the confidence interval in a minute, but here's a note. This test result is not very definitive. The p-value is very close to alpha. In reality, one would probably do more tests by giving the dog another bath after the fleas have had a chance to return. Yeah, or maybe even find another dog if you have more than one dog and give them a bath and see how well they did, percentage-wise and proportionately, and then see how that goes. But this, in other words, it was sitting almost right on the borderline. It's time to redo a test again, or funding for more testing would be warranted. That's what we used to do with the Forest Service and UCR as a grad assistant. Whenever we got something that way, it would just say, further funding is required for more details, or words to that effect. Oh, we don't really have to do the confidence interval here. That's just a review of prior material, but I did actually work that out. That would be based on prior material. You start off with P prime being the center value, plus or minus the T value, which I got to about 2.02 times the standard error in terms of P prime and Q prime. And that worked out to be very close to this number here. We'd expect 95% of the time for it to be between 0.26 and 0.55. And yeah, the 0.26 is not really included there. So that's why we have a bit of a disconnect on this. So yeah, it should include the 25%. If the confidence interval overlaps with the number, then we've got HO for sure. But this one just barely missed the number. My numbers were actually a little closer than this. I need to double check it. I got about a 0.252, which rounds as 2.25, but that still does not include the 0.25. That just shows you from another perspective how close this was. But we still don't have HO here. We just don't have it. I'm sorry, we don't have HA here. We do not reject HO. I misspoke, but I know what I was thinking. So HO is under control. We do want to just keep the same shampoo. Maybe next time it will not be 40%. It might be more like 30% or even 22%, something like that, instead of the 40.5% that we got. Do we have time for another one? I guess we might. Let's take a look from the calculator point of view, and that might be it for today. I'm hitting almost the hour mark, I believe. So the National Institute of Standards and Technology provide exact data on conductivity properties of materials, and here are the measures for 11 randomly selected pieces of a particular type of glass. And so these range from, 0.95 up to 1.11, 1.12. Okay, is there convincing evidence that the average conductivity is greater than 1, alpha 0.05, assume that it's normal population? Four-step process to answer this question. So we need to see if it's greater than 1. So the main hypothesis, the alternative, is greater than 1. And I would just say equals 1. take my advice. If you happen to do it the book's way and get steered in the wrong direction, don't blame me. I'm trying to help here. But if this makes perfect sense to you, please go ahead and use it. I will not worry about it if you go through the correct procedures. Have a plan. So we're testing a sample mean without a known population standard deviation. All we have is data. That's it. So we don't have a known sigma. At least it wasn't given to us. So therefore, we have to use a t-distribution. So that's important to decide what distribution you want. The answers may be close in nature, but I will be able to tell if you use the wrong distribution or not. Generally, you'll lose around half credit for picking the wrong distribution, even if the numbers are quite similar. And there are times where they're painfully similar, very, very close, but I can always tell the difference. So please pick the right distribution. That's one of the first things you have to do. So here we entered in the calculations on the calculator, and as you see, 1.08, et cetera. So these are the last few numbers, and so they have us go through and hit various screens. Of course, you do stats, edit, and L1 to get your numbers into the data set if you're using this calculation. Then hit stats, and then t-test. You know it's a t-test, and I'll go for data first, and that's where the input came from. You don't have summary statistics, as many problems do. I tend to get you the summary statistics most of the time. I'm not going to guarantee it 100% of the time, but I tend to lean that way strongly on exams. Anyway, the mean is meant to be 1, as they said from the hypothesis. The list, of course, in case you had more than one list, that's L1. And frequency, each one of these only happens once, so there's no double ups or anything like that. And we are going greater than mu0, as we saw earlier. Yeah, greater than 1. Don't even pay attention to HO. It's pretty much always the same. So when you hit calculate, what you're going to get is for the hypothesis where mu is greater than 1, here's a t-value, a little less clearly defined than z, although it has similar highlights from z. That's more than 2 standard deviations away on the t-scale. That gives us a pretty small value of p. The p-value 0.0359. I usually round to 4 decimal places. Because our mean, which is also important, was 1.04. That looks pretty close to the 1. And there's a standard deviation if you want it. Of course, there's your n if you want it, and all that stuff is given. And then the picture, as you go into draw instead of calculate, so you have to pretty much start over. It'll hold your data for you, and everything is the same. Just leave it all alone. Just click down to draw and circle that. Of course, then you'll get a picture, not an extremely high-tech picture, but it does give you the t and the p, as you already saw. This being a right tail test, it'll shade in the upper 4%. And of 3 decimals, p is 0.036. That is less than 0.05. Remember, alpha was 0.05? And so this is rare compared to the pretty much ordinary level of 5%. So rare enough. We will reject HO here. We found something that's rarer than expected. So we're able to handle that. And when we reject HO, we basically use HA as our default position, and we then are believing now that the mu is greater than 1, even though it didn't seem to move the needle much. That 1.04 was moved. Our standard deviation was pretty small. Those numbers were pretty tightly arranged. When you take a close look at the numbers, there's not much of a difference there. That leads to a small standard deviation, and that means the 1.04 really is important. If these numbers were all over the map, like between 0 and 3, then your 1.04 would not be very important at all. And they're missing a comma here, another little typo I notice. But because these numbers are tightly bunched, moving it even just 0.04 away from the 1 to get a 1.04 is important, and it does make a difference. So, and if you need to know what that standard deviation is, the calculator will also tell you that as well. You can double check the calculation if you like, but there's not too much need for that. I've been running through some of them, of course. Anyway, it's reasonable to state that the data supports the claim that the average conductivity level is actually greater than 1. We didn't say how much greater than 1, but it is greater than 1. How about that? We have a couple of other examples. I guess I can go through one more of them. We'll see. I think the cell phone one is an interesting one. It's got some pretty big numbers. So let's take a look. This was a study I've seen before. For a while there, several years ago, they seemed to think there was this thing flying around as things do on the internet, which are often not well documented, and yet they seem to alarm people, and so alarming things get publicity, et cetera, et cetera. And so they thought, oh, perhaps cell phone use caused brain cancer. Does it? Let's find out, shall we? 172 of these subjects developed brain cancer out of 420,000. Well, okay, is that enough? I don't know yet. So test the claim that the cell phone users developed a brain cancer at a greater rate than for non-cell phone users. That's important to set up the non-cell phone users. And by the way, their rate is 0.0340%. We'll put that into a decimal in a minute. That's even smaller than it looks. And now they pick actually a very small alpha. So we'll see how that goes. We need it to be pretty far out there. So I'll explain why it should be so low. We'll get to that in a minute. Let's take a look at the solution here. Four-step process. We are interested in it being greater than the non-cell phone user rate. Here it is in percentage, or I'm sorry, proportion. Proportion. Just put a couple of extra zeros in there, 0.00034. And the background null hypothesis is just equal, to that number, or even less, but equals is sufficient. And even that leading zero is not necessary either. And if you committed a type 1 error, you're accepting a false claim. And the claim describes cancer-causing environments. Not very good. So we certainly are not interested in that. We want to minimize the chance of incorrectly identifying causes of cancer. That's not a good thing, to misidentify something and continue down that bad road. Okay, so we are really narrowing that alpha. So very, very small. Okay, so part 2. We'll be testing a sample proportion with 172 quote-unquote successes. That's a stretch. But anyway, that proportion is the sample is sufficiently large. You look at NP, and you do get about 142 or so. And the other is like 400,000, so they're both above 10 or both above 5. They're actually fine. And 2 independent outcomes, and fixed probability of success is this number here, 0.00034. And so yes, we can go ahead and use it. And here are the TI results as found on the calculator. These last examples are from stats and then test 1 proportion z-test. We're going to save the 2 for chapter 10, 2 proportions. And in fact, in the way we are using 2 proportions, so we didn't set it up that way. So this is only a 1 proportion test. And so the proportion should be greater than, and they put it into scientific notation. I just shouldn't use the decimals. They can use all these decimals, but yeah, they can't let us use that decimal. That's a little inconsistent. Okay, well anyway, when we put it to be greater than the number, and it's a right tail test, remember, we have to see if we can get a little bit more or somewhat more than that non-cell phone user type of brain cancer situation. Yes, there are people that still don't use cell phones. Okay, the z is 2.44. That's a pretty strong z. Our p-value is 0.0073, rounded to 4 decimals. Okay, that's kind of rare. Not going to happen on its own very often because we do have the needle moved. And incidentally, we never found what that proportion was. But I did. I found it was 0.0073. And I don't think they even say it anywhere, which is... Oh, there it is, finally. Well, yeah, okay, we got a p hat. I misspoke. I'm sorry, I misspoke. P hat from our sample, which was the original numbers given. Here it is, 172 over 420,000. That is a proportion of 0.00041. I think it's good to see numbers like that. I can't believe they're hiding them. And that 0.0041 is a little bit bigger than 0.0034. But is it enough? Well, looks like it just might be. Z is 2.44. The P is 0.007. But here's the thing. We had a very stiff bar to try to cross. We had to have it beat the 0.005 or be less than the 0.005. And this is actually greater than that. Yeah, we got a pretty strong p-value, but we really raised the bar. It depends how you look at lowered the bar. Well, this is a very strict number. Very strict, and then we didn't make it. Here's our picture from the draw command, here's the p hat. That's the number I was trying to refer to. It was 0.00041 in ordinary decimals. No need to go for the e notation yet. Of course, a very large n, which really solidifies our numbers down. So we got it down to a very small chance of this happening by random chance, But yet we needed to get even smaller. And because we couldn't do that, we can't reject HO. We're not going to reject HO. And what did HO say? It said that essentially P is still the same as it ever was. Keep the status quo in place. Same as before. So we will say that there's not enough evidence to support the claim of higher brain cancer rates for the cell phone users. No, there just isn't. We got slightly more, which didn't really matter. On first glance, with 400,000 people, it looked like we had a low p-value, but then, of course, they will correspondingly change the bar, the alpha is what I'm trying to say, down to a very small number, because they don't want to make a mistake on this. This is a pretty serious situation. They got a huge sample, which is good. They got a certain number, a little bit more than they expected, but not enough to make a difference. That's the main idea here. Not enough to make a difference. And yes, there's another one. Maybe I'll have time to look at this example about another huge sample with 268 million people in the sample. If we have chance, we'll come back and get to that another day. But we've essentially finished up, chapter 9. And that means when we come back live next Monday, which will be the 26th, we will start chapter 10. I do want to cover chapter 10. It's very similar to before, except now we have 2 samples. So I'll cover at least a portion of chapter 10. I'm required to cover part of chapter 12. So 11 is kind of on the bubble right now. I'm not sure if I'm going to get to 11. Hopefully I'll get to at least a little bit of it, even if it doesn't show up on the test. We'll just have to see how the time goes. I'm down to about 4 more lectures. So it just depends on how fast we can go. I knew 9.5 would be a long one because they actually had lots of good examples here. So I'm happy about that. Not entirely happy with sometimes how they present it, but besides that, I'm not unhappy with how it's going. Okay, so I guess I'll let you go for now and have a nice, rest of the week. And if you're watching this on Monday, very good. If you're watching it earlier, great. A little bit later, okay. But you should be caught up by the Wednesday lecture at 4 o'clock. Back live Wednesday at 4, and we'll talk to you soon.